on the theoretical aspects of dark matter. In that, first I will talk about types of dark matter, and next about structure formation in our universe, and the final one would be voids in the universe. First, types. There are two kinds of dark matter in the universe. First one is hot dark matter, and the next one is cold dark matter. Hot dark matter. Dark matter whose kinetic energy is much larger than their rest energy is called hot dark matter. It means they are very light, and so they can move with almost speed of light, and it is called relativistic particles. And one of the candidates for hot dark matter is neutrinos. However, since the experimental upper bound for mass of neutrino, it was revealed that hot dark matter is not enough to provide predicted mass of dark matter. However, but it exists. Next one is cold dark matter. Dark matter whose rest energy is much larger than their kinetic energy is called cold dark matter. It means they are very massive, so they are very slow, and called non-relativistic particles. One of the candidates for cold dark matter is meteors, and the example of meteors are something like brown dwarf or black hole, something like that. And also another candidate is neutrino. It is a kind of supersymmetry particle. Next is about structure formation in our universe, and it is the picture of our universe. It represents the whole vision of a visible universe, and it is very large scale, so each small point in this picture can form the galaxy, large enough to form the galaxy. And at the dark region means that the density of matter is higher than average, so they can make clumps. And at the bright region, it means the density is lower than average, so they make the void in this picture. And it is the kind of history of universe, and this axis means scale of time, and each hoop represents the shape of universe in corresponding time scale. And as we focus on the earlier universe, there is a time when explosive extension of universe, and it is called inflation. And after inflation, the universe becomes extremely homogeneous and isotropic. Homogeneous means matters are uniform all over the universe, and isotropic means independence of direction. However, there are still some fluctuations called quantum fluctuations. And there are also dark matters, and as we can see in this graph, those are 4% of total mass are called barren matter, which are well known to us, such as protons or neutrons, something like that. However, dark matters are over 20%, so dark matter is 5 times much more than that of barren matter, and so they can make the gravitational potential like this, and at the center of this well, the dark matter pull down the other barren matter, so they can dominate the motion of other barren matters. And hot dark matters contribute to formation of large-scale structure in our universe. They are very fast to form galaxies. So since they are very fast, they are not gravitationally binding to other barren matters, and they free streaming out through the universe. So they can enlarge the scale of quantum fluctuation, and they damp the small scale of fluctuation. Here, the small means galaxy scale. So they are smallest size to form the clustering in supercluster or. And next is cold dark matter. They contribute to the formation of galaxies. Since they are very massive and slow, they can strongly gravitationally binding to other matter, and they can form clumps in the universe. So they can amplify the amplitude of small-scale fluctuations, and they can form the galaxy. Then it looks like reasonable to combine two dark matters to form mixed dark matter model. However, it was revealed that it's not true. Mixed dark matter model was favored until 1990s. However, the scientific revolution accelerating universe was revealed in 2001. As we can see in this picture, not only inflation time but also recent universe expansion is also accelerated. And the cause of acceleration is revealed as dark energy. They contribute to total 70% of total energy in the universe, and they can accelerate the expansion of the universe. So the now new model is called lambda core dark matter model. Here lambda represents the dark energy. So next I will talk about the voids in all universe. It's a kind of picture for simulation of formation of structure in all universe, and they visualize some underdance rhythm is circles, and never mind the characters. And as there are some density fluctuation, there will be some rhythmic positive fluctuation. It means the density of that rhythm is higher than that of average. And with negative fluctuation rhythm, the density is lower than average. So we can think about each underdance rhythm of baryon emitter and dark matter. And the important thing is that there is a difference between area of two rhythms. As in this picture, the outer parts are large-scale structures, means very high density. And the large circle means underdance rhythm of dark matter, and inside small circle means underdance rhythm of baryon matter. And their common rhythm is called void, with very low density. And as dark matter can work clock better than baryon matter, as we move from central void to the large scale structure, there is some intermediate rhythm between void and large scale structure. It is called transition zone. And the transition zone is large enough for production of galaxies. So the amount of dark matter in galaxies can be varied from galaxy to galaxy. And now let's finish it. The friends, is there any questions? No? Thank you.